Well, in this example, we're going to use the universal law of gravitation to calculate the acceleration of gravity on the moon. Here's how that works. First, we'll write down the universal law of gravitation. F is equal to g, the universal gravitational constant, times, I'll say m1, times mp, that'll be the mass of the planet, over the radius of the planet. So we'll assume this is close to the surface of the planet. Now we're also going to write down Newton's second law, force equals mass times acceleration, or we could call it F equals mg, g will be our acceleration of gravity. That's Newton's second law. Now if we think about that, F is equal to the mass of the object times the acceleration of gravity. And if we go back over to the universal law of gravitation, it must be true then that g times mp over r squared must be equal to the g in Newton's law. Think about that for a second. So if we plug that in, we get 6.676 times 10 to the minus 11th meters cubed per kilogram second squared. Multiply that by the mass of the moon, which is given above, 7.384 times 10 to the 22 kilograms. And then divide everything by the square of the radius of the moon, and I'm going to have to convert that into meters, so it's 1737 and 3 zeros in meters, because there's 1,000 meters per kilometer, and don't forget to square that. My units cancel like this, kilograms, kilograms. The meters squared below cancels one of the meters cubed, sorry, 2 of the cubic meters above. So I have units of acceleration, meters per second squared. So now I just need to do that calculation, and that comes out to be 1.63 meters per second squared. Now, if we compare that to the acceleration of gravity on Earth, 9.81 meters per second squared, just divide that in, we get approximately, it goes in about 6 times. So indeed, the acceleration of gravity near the surface of the moon is about 1/6 of that on Earth. So on the moon, you would feel like you weigh about 1/6 of what you do on Earth.